Hi everyone! So I wanted to make a couple videos to go along with the reading. The goal is that after you finish writing up the lab, you'll watch these and do the reading, and that will give you enough context with the next topic, which is momentum conservation, so that when you come to class on Monday, you'll have a basic idea of the theory, probably a few questions, which is great, but we could start there rather than spending half the class introducing all the theory. You will have been exposed to that before, so please take some time to watch these. I won't be offended if you scroll through a little faster or you watch them on double time, but I think watching them will be helpful, because then we can pick up on Monday and really spend more of our together time working on problems rather than just listening to me talk about physics. Okay, so here we go. I'm going to sharpen my pencil and get started. And I'm going to start where we left off at the lab. So in the lab, we saw that the velocity of the center of mass, you got a little practice working with this equation, right? Which was good because I think it felt a little mysterious. But now hopefully it feels a little more familiar what you're doing when you take all the individual masses, multiply by the velocities of each mass, and then weight it by the sum of all the individual masses, or the total mass of the system. That gives you the velocity of the center of mass. What you saw in the lab was that the velocity of the center of mass when two objects collide is constant. It doesn't change. It's the same velocity before the collision as after the collision. So even though the speeds of the individual masses themselves change, and might even change direction, the velocity of the center of mass will always stay the same. That's a direct consequence of the fact that the system is isolated. That wouldn't be the case if somebody was pushing on the system, but we saw earlier this week that when no external forces act on a system, the velocity of the center of mass is constant, because the center of mass itself will not accelerate unless there's a net external force acting. Now, when two objects collide, it doesn't mean there aren't forces exerted. In fact, object A exerts a force on B, object B exerts a force on A, so they exert equal and opposite forces on one another. But because of Newton's third law, those forces are equal and those forces are opposite. And so even though they can each individually change their own behaviors, together as a system, there is no external force. And so that center of mass velocity, despite changes and transfers between the two objects, will not change. This becomes a little more familiar when we multiply the mass up there. We get mass times the velocity of the center of mass equals the sum from I equals 1 to n, mi vi. And we will recognize this as the momentum of the center of mass. mv is momentum. We learned that. Well, you learned that last year, but we reinforced that in the last video. Oh, this is so messy. Okay, there we go. Now this is the individual momenta of each object. And so what it tells you, if the velocity of the center of mass doesn't change, it means the momentum of the center of mass is constant before and after the collision, and also that the momentum of the center of mass is just the sum of the individual momenta of the objects. And remember, this isn't a straight sum. This is a vector equation. So there's an x version, there's a y version, and then these can be positive or negative. So, they might add and subtract, but we call it a sum. But remember, they're vectors. Last year, you remember, we told you that the momentum of the system was you add up all the momenta in the system, but what we were really talking about when we said system was center of mass. And so this really is a more rigorous result about how we describe the center of mass of a system of particles. The system's momentum is the momentum of the center of mass, and it's the sum of the individual momenta of each individual particle, the vector sum. And as long as no external forces act, the velocity of the center of mass, and therefore the momentum of the center of mass of the system, cannot change. Well, let's take that a step further. If the left side of this equation can't change, it means whenever I decide to add these up, they'll always add up to the same number. And so if I look at a situation for the momentum of the center of mass before the collision, and then I look at it, I'm going to use initial and final, before the collision, or initial, and I look at the momentum final, they're going to be the same, because no matter how I add them up, they're going to be the same number. And this is what we know as momentum conservation. It's a direct consequence of the fact that the center of mass velocity will not change in a collision. And I think that's a great way to think about it, and a very powerful way to think about it. So let's look at a couple of quick examples. Let's look at a one-dimensional example. And this one I'm going to make super simple because they're all pretty straightforward one way or another, so let's just keep it as a simple example. There's no need to make this one complicated. Let's say I have a block of mass 40 kilograms at velocity equals 0, and I have a man on ice skates pushing on the block, and he's got a mass 80 kilograms, and he's also at velocity equals 0. That's our before picture. He gives the block a push, and the after picture is going to be the block, 40 kilograms, moving at 8 meters per second to the right. What's the velocity of the man after the collision? What is he doing? Let's call it v. And let's, you could probably guess it's going to be backwards just from intuition and experience, but let's not assume. The one thing about momentum that I'd love to stress with you is don't assume. When you know something's in a given direction, assume it's in that direction. Sometimes it's counterintuitive, and if you try to guess the direction, you might guess wrong. Always let the negatives and positives pop out of the equation just from working it out. Sometimes you'll be surprised, and that's kind of fun. All right, let's apply our momentum conservation here. Even though we could probably reason this whole thing without equations at all, let's look at momentum initial equals momentum final. And let's now think about how we're really applying the center of mass equation, the momentum initial, the mass of each object initially times its initial velocity, adding them all up, and then doing the same process after, adding them all up again. Well, the initial is pretty easy. It's 80 times 0 plus 40 times 0, which is 0. And what is it after? Well, let's do the same thing again. It's going to be, oh, first important, you have to choose a positive direction and stick with it. I'm going to choose to the right as positive. So 40 times 8, 40 I should probably be good about my, I'm going to be good about my units. 40 kilograms times 8 meters per second plus 80 kilograms times v. Notice I didn't do minus. That's what I was talking about. The v is going to tell you if it's negative. You don't need to force it to be negative. Let it be itself. So I get that equals 320 kilogram meters per second plus 80 kilograms times v. And then negative 320 equals 80v, and v equals negative 4 meters per second. And so that tells you, as you would have expected, that the man recoils backwards. And again, let it tell you, don't force it to do its thing. So that's one way, that's one dimension. Let's now look at a different situation, ones that we didn't really do last year. Let's look at a case of I have a little ball, let's say it has mass 2m, and it's approaching at a velocity of, we could stay with 8 meters per second, and it's approaching a slightly offset ball of mass m that's initially at rest. They collide, but they don't move off in one dimension, they go off at angles. And let's say you're told that the 2m after the collision is moving upwards at a speed of 4 meters per second at a 30-degree angle, and you don't know what m is doing. And let's pretend we really don't know. We can probably guess it's going to be down and to the right, just based on this picture, but let's pretend we don't know. Let's say it has, a Vx and a Vy, and we just want to figure out what they are. So now we have a two-dimensional problem. Remember what I said, when you're doing a two-dimensional problem, you have pi in the x direction is pf in the x direction, and pi in the y direction equals pfy in the y direction. So you have to apply momentum conservation separately in each direction. And I think that there's a number of ways you could deal with the vectors. I think that's the easiest way to deal with the vectors. So let's take a look here. First, we're going to have to get our components of this guy using sine and cosine. So if I do this one, I get, what do I get? Here's my calculator. I get 4 cosine 30 for the x direction, 3.46, and that's to the right, And then for sine 30, I don't need my calculator for that, that's 2 meters per second up. And I'm going to now set my coordinate system as to the right and up as positive. I'm going to sharpen my pencil again, and I'm going to apply momentum conservation. So first I'm going to do Pix equals Pfx. And so my Pix is going to be 2m times 8 meters per second plus 0 for this guy. And then my Pfx is going to be 2m times 3.46. I don't know why I made that 6 so super tiny. 3.46 plus m times Vx. And I'm not going to force it to be anything. I'm just going to let it come out the way it is. The first thing you'll notice is the m's will cancel. So often in these problems you're not actually given the mass, just the relative masses. And I get 16 equals 2 times 6.92, 6.93, if I use the thing all the way out, plus Vx, and 16 minus 6.93 is 9.07. And so it came out positive, which makes sense. I expect that to be going to the right. Now let's do Piy equals Pfy. Well, Piy is easy to calculate because nothing's moving in the vertical direction initially, so my Piy is just 0. My Pfy is going to be 2m times 2 meters per second plus m times Vy, and again I know that's going to come out negative, but I'm not going to put the minus in here, I'm going to let it pop out that way. My m's are going to cancel, and I get Vy equals negative 4 meters per second, and again that's consistent with what I would expect this to go down. Now the last step is just to get the actual, here's m after the collision, here's the v, here's my 9.07, here's my 4, I want to get v, and I need to get the angle to specify the velocity. So I need to do the Pythagorean theorem, 9.07 squared plus 4 squared, and then I take the square root of that, I get 9.9. And then I'll do inverse tan of 4/9, second tan, 4 divided by 9, and I get 24. Okay, so that's how you apply momentum conservation in 1 and 2 dimensions. You'll notice in both cases, with just the single equation of momentum conservation, I had to tell you something about the after. Here you knew all the before, and I told you something about the after, so you had one unknown. Here, same thing. Oops. I told you something, you knew the before, and I told you something about the after. If these two stuck together after the collision, for example, then I wouldn't need to, then you'd only have one variable to figure out, so it would work. But when you have two things at the end that are unknown, you have to be told one of them in this situation. We're going to see in the next video that actually you don't need you can, with other information, other constraints on the problem, like energy conservation, you don't need to use, you don't need to know anything about the end, but those are only very specific cases where both momentum and energy would be conserved. Let's take a quick look here, just on that note. Let's take a look at this situation. What was we know momentum is conserved in every collision. That's non-negotiable. What was the kinetic energy before the collision? Well, nothing was moving, so the kinetic energy initial was 0. Here, both things are moving. And remember, kinetic energy doesn't care which way you're moving. It only cares that you're moving. And so we have a whole bunch of kinetic energy at the end. And so this collision is not elastic. Elastic collisions are collisions where the kinetic energy before is the same as the kinetic energy after. And this one, the system actually gained energy. And you could say, where did that energy come from? From the chemical energy stored in the man's muscles as he pushed that box and also moved him backwards. It came from chemical energy. It was stored there. But sometimes people call this a super elastic collision because the system actually gains energy. It didn't really gain energy, it just took it from stored chemical energy. But it's not an elastic collision. So here, I didn't make it elastic, I just made up these numbers. So my guess is if we did the kinetic energy of this, 1/2 times 2m times 4 squared, and 1/2 times m times 9.07 squared, that's going to not be equal to the kinetic energy before the collision. So this would also be an inelastic collision. The kinetic energy would not be the same. Momentum will always be the same. You can never assume energy is conserved. And that's why, just knowing that momentum is conserved, I need to know something else about what they're doing at the end to solve it. However, if I know that it's elastic, so I know that the kinetic energy is the same before and after, then I don't need to know anything else about the system, but it means I have to do a ton more algebra. So stay tuned for that. Okay, bye.